So we've talked about data visualizations, the scatter plot, and we've already started to think about the strength of the association. But if we wanted to really quantify the strength and direction of an association, we could use a statistic called the correlation. And as with everything in this class, we have the sample statistic, the one that we can compute based on our real data. And then we have the population parameter, what's going on in the big population that we probably will never see and never truly know. So for the sample statistic for correlation, we use R. We typically use a lowercase r. And then for the population parameter, we use the Greek letter rho. So it's sort of like a P. You start at the bottom and you loop around. So if I look at these same pictures that I was looking at before, I can see that this association that we said that was, positive and moderate strong, that's got an R of 0.91. This one that we said was moderate weak, that's got an R value, a correlation value of negative 0.55. This one that we said was kind of moderate and positive has a correlation of 0.49. And this one where we were like, it's pretty weak, but maybe there's a negative relationship, it's got a correlation of negative 0.04. So look at those numbers for a minute and see if you can see anything that relates the correlation value to the picture, and if you can glean any facts that you think are true about correlation. And then we'll talk about them. So you might have noticed that correlation has to be between -1 and +1. You're never going to have a correlation that is less than -1 or greater than 1. And the sign of the correlation indicates the direction of association. So if you have a positive R value, that's a positive association. If you have a negative R value, that's a negative association. And if the correlation value is about equal to 0, that's no association. So back to this one, this is negative 0.04. I might say that's about 0. Maybe there's no association. It's just kind of randomness all the way across. The closer the correlation is to plus or minus 1, the stronger the association. So I think we saw that here. This one was a pretty strong association that had a pretty big R value, and then the ones that we said were more moderate had smaller values in absolute value. Correlation has no units, and order doesn't matter for correlation. So if I was going to find the correlation between accept and enroll, that would be 0.91, and enroll and accept, that would also be 0.91. It doesn't matter which one you think about first. So there's a guessing game to try and guess the correlation from a picture. And it turns out researchers have found that humans are not super great at guessing the correlation. So this isn't something that I would expect you to do like on an exam, be able to look at a picture and guess accurately what the correlation value is. But researchers have also shown that you can get better at this if you practice, and the guess the correlation game is one of the ways that you could practice. So I think we'll play this when we are in synchronous class, because it's a little bit more fun when I have people helping me out with my guesses. But maybe I'll just show you a preview of what the game looks like. So I'm going to do a new game, and I will call myself Dr. McNamara. Okay. And I've read the privacy policy before. So I'm going to do a new game. It's going to give me a picture of a correlation, and then I'm going to guess what I think that correlation is. So this one looks kind of positive, but weak to moderate. So I'm going to guess maybe 0.3. And it was 0.35, so that's decently good. And then I could go on next. Okay, this one also looks positive. It looks a lot stronger. I might go 0.85 and guess. 0.86. So I'm pretty good at this game, but we will play it together as a group. So, one thing you have to be careful with when it comes to correlation is the influence that outliers can have on the correlation. And so in this case, I'm using real data, so I think that this effect isn't as strong as it could have been if I had made something up with a really, really big outlier. But my data set about colleges had this point way out here, and this is Rutgers, and they get a ton of apps, way more applications than like anyone else gets, but they don't enroll as many as some of these other schools, and so they look like an outlier. They're pretty different from the rest of the data. And so if I have Rutgers in the mix, my correlation value is 0.85. But then if I take out Rutgers, and that's what I've done over here, then my correlation value is 0.87. So the correlation gets stronger. I think you can also see that the axes in my graph changed. Instead of having my maximum be 50,000, now it's only, a little bit more than 20,000. So that makes a difference. So you have to be careful. So there are some correlation cautions. One is that correlation can be heavily influenced by outliers, so it's really important to plot your data. Another one is that correlation only measures linear association. And again, that means it's really important to plot your data. There is this set of plots. They used to be called Anscombe's quartet, and they were things like this. But then someone realized that they could make a dinosaur, and so there's a whole set of plots that are called the Datasaurus plots. And the idea of these data sets is to drive home the point that you really need to plot your data. If you just calculated the correlation is actually the same for all of these plots, or just about the same to a rounding error. But when you look at the plot, you can see that there's a really different pattern going on. So this one looks vaguely positive, this one looks vaguely negative, this one looks like a star, and then this one down here looks like a dinosaur. So you really need to plot your data. It's also important to remember that correlation does not imply causation. So there is a whole website on spurious correlations. I just pulled one of them here. There is a pretty strong correlation, and apparently I didn't include the number on here, but between the number of math doctorates awarded and the amount of uranium stored at US nuclear power plants. So do we think that if we suddenly started giving fewer PhDs to people in math, that we would have less uranium at US nuclear power plants? No. Those things are actually not related at all. So there's just a correlation by chance. And then we talked a few sections ago about the idea of confounding variables. So if there's a confounding variable, then that might explain the relationship between two variables. So it's really important not to look at a strong correlation and say, that means that this causes that. You can only imply causation if you have a random experiment, and we very rarely have those.